Okay, this is going to be the last video in this series, and we're going to do a practice one together. We're going to take everything we talked about and see what we can do. So from above, hopefully you've noticed that the only thing that we really care about is the vertex. Our vertex is going to be our key part. So the first thing I'm going to do in this function is I'm going to identify my vertex. I'm going to take the opposite of my x value, so -3, and then just perfectly take my k value out to the side. -4. We know our x's do everything opposite. That's why I made it negative. We know our y's do it just like they're supposed to. That's why it stayed the way it was. The other piece of information that I do need to know is whether or not this parabola is going to open up or down. And I can see that because my a term is positive, it's going to open up. So I'm going to come over here. I'm going to find my vertex, -3, -4. And then I'm going to open this function up. And once again, it doesn't have to be perfect. We're just looking for a sketch here. So this is looking at the entire function itself. But I know that we're going to eventually want to make it invertible. So this is that idea. It says, what is the domain and range for which the function is invertible? As soon as I see that word saying, hey, if I want to invert it, I know that I must restrict the domain. I must cut off half. Well, we now know that we're going to cut off the left half. So this is -3, -4. So my invertible domain, the domain that I'm going to use to invert, is from -3 to infinity, and that range is from -4 to infinity. So I'm going to put this part back in as a separate color because we know that it does actually exist. That's not my best parabola, but it's going to be okay. We know that this does actually exist, but when I'm talking about the invertible domain, we're only talking about this portion here, the right-hand portion. So if I'm only looking at -3 on, then it is invertible. Part B says find the equation for its inverse function and then sketch the function. So we're going to do the inverse equation in just a second. Let's talk about the sketch here. So we know that we are taking this part here and we are reflecting it across the line y equals x. Well, that means that my vertex number is going to change. It's going to be -4, -3. So -4, -3. And we should know now that the general shape of a square root function looks like this. So I took my right-hand side, I switched the value of my vertex, and I reflected it across the line y equals x, which is what gives me the top portion of this sideways parabola. Even if I were to go ahead right now and find the domain and range of this, the domain of my inverse, so I'm going to say the domain of -1 because this is my inverse. Well, now the x value is -4, opening to the right, so infinity. The range, well, now the y value is -3, going up, so to infinity. And I can see that once again, these swapped, which is what we're looking for. So this is one of the key parts. Can we find the domain in which it makes it invertible? So can we restrict the domain at the vertex? What is the range? And then when we do the inverse, what becomes the domain and range? And it's just a perfect swap here. Last but not least, let's go ahead and find the equation. So we had originally f of x equals 1/2 x plus 3 squared minus 4. We know that when we're finding the inverse, what we're really doing is isolating the other variable. We're making what was the input become the output. One of the first things I'm going to do in order to do this, I don't like doing it when it's f of x. That just kind of confuses me, so I'm going to make that a y. And then we can go ahead and isolate. We isolate using SADMEP, which is our opposite order of operations. So I'm going to add the 4 to the other side. Now I'm going to get rid of the 2, the 1/2. Dividing by 1/2 is the same thing as multiplying by 2. So I'm going to bring that up to the other side. And once again, we are trying to isolate the x. So I'm getting rid of things on the side. We're now ready to get rid of the square by square rooting. So now I have x plus 3 equals the square root of 2y plus 4. And the last thing I'm going to do is move my 3 over. So I'm going to come up here. I have x equals the square root of 2y plus 4 minus 3. I'm super close to being done, but now that I've isolated it, I need to show that this is just still a function, and we know when we're just graphing on an xy plane, our number over here, our input, should be x, and over here, our output should be some variation of y. In order to do that, I'm going to show that it's the inverse, so I'm going to switch it to f negative 1 of x. That means it's the inverse function is equal to the square root of 2x plus 4 minus 3. So this is actually my equation. Once again, that last step is making sure that the variable that's acting as the input goes back to being x, and the variable that's acting as an output goes back to being some form of y with the inverse notation on it. Also, we could quickly see here that we did have the correct vertex. From the inside, we're going to do the opposite with our x, which is negative 4, and we're going to keep our y exactly as it is, which is negative 3. So this is an example of being able to restrict the domain. Notice once again, to start, we only cared about the vertex and whether or not it was opening up or down. We then restricted to the right-hand side of the vertex. We found the range. Those two flip-flopped when we looked at our inverse. We did a quick sketch of a square root function. And then we also did the math and the algebra out to figure out what would be the equation of this function.